Hello everybody, today we're going to be going over the chain rule, specifically when there are multiple chains, and we'll look at that more during the example. So just to review, the chain rule is used to differentiate composite functions, which means when there are functions within other functions. So this is kind of what that looks like. If there's a f of g of x, that's going to be split up when we're differentiating to f prime of g of x times g of x. So I'll hand it over to myself and we'll do that example. Alright, so we're going to start out with a pretty easy question to kind of get the hang of everything. So we see how this starting function gets split into two parts. We have the cosine x squared that moves down here, and then this is that second part of the chain that'll move here. So we find the derivative of the first part while keeping that second part intact, and then outside of it we're finding the derivative, and that's what that looks like. So then when we clean it all up, we're going to bring the 2x to the front and have this part at the end.
Go for it.
Is it filming? Alright. Now we're going to go over a problem with multiple chain rules. So we start out at the top with our original function. And what we're going to do is we're going to split it into this. I've color coordinated so you can kind of follow along how everything gets split apart. So within our function, we're going to take this part and take it out because this needs the derivative, that inside function. And we bring the 4 down just like the power rule says to do. Then we're going to find the derivative of that. What we don't want to do is stop here because this is another chain rule in itself. So that's why we have this second x squared. So that's our first do. Do remember to write the whole problem. Don't stop after one chain rule. When we're doing that, we're just going to do that whole system again. And you can see how those numbers work down. We take these monomials and bring them to the front, so we end up with that 24. So that's the second do. Do simplify, and don't forget to move the monomials to the front. And that is how we end up with our final derivative.
The implicit differentiation is a calculus technique used to find the derivative dy over dx of an equation where y is not explicitly solved by the term of x. By treating y as a function of x and applying the chain rule to all the y terms, you differentiate both sides with the respective y to solve dy over dx. You can use this technique to find the slope of the tangent line dy over dx for curves that are not functions or are difficult to solve for y. This is an example that we are going to be solving. So first you're going to do the chain rule for the y's and the x's. Don't forget to do the chain rule for your y's. Don't treat y as a constant. After that, you do have to add your y prime to both of that sides. Then you add all your y's on one side. Then you're going to divide that y prime out. You're going to divide by this big group. Divide both sides. You have to divide both sides. One thing you do on one side, you do the other. After that, you'll have y prime equals that. You turn that to your dy over dx, and your final answer is that.
Hi everyone, so today we're going to be learning how to separate integrals and add them, which allows us to solve these larger, big, more complex equations in an easier way. So a few things you need to know. If you're going to switch the limits, and you also need to switch your signs. So if it's positive, you need to switch it to negative, and if it's negative, you need to switch it to positive. But only do this if you're going to switch your limits. And then also, remember, this only works for a continuous function. Alright, let's try a problem. So given that f is continuous on the functions the integral of -3 to 6, f of x dx equals -3, and the integral of -3 to -8 f of x dx equals 1, what is the value of -8 if the integral of -8 to 6 f of x dx? So we're going to start off with going the integral of -3 to -8 equals 1, but we need to switch the limits so that it's -8 to -3, and that will also switch your sign to -1. Once you do that, you're going to set up your problem, and you're going to go -8 to -3 f of x dx, and the integral of -3 to 6 f of x dx equals negative 8 to 6 f of x dx. Once you have it set up, then it's pretty easy. You just plug in your values. So you're going to take your negative 1 that you got here, and then adding it by your negative 3 from up here to equal negative 4. So that the integral from negative 8 to 6 of f of x dx equals negative 4.
Hello, today I'm going to be going over linear approximation. And to start, I'm just going to give you a quick explanation on what it is. So, when you're given a complex curve, instead of trying to calculate a value on a complex curve, we use the equation of the tangent line at a nearby point to estimate the value. And this works because values that are very close to the point of tangency, their y values are nearly identical. So, in the next part, I'm going to do a quick example problem where I'm going to give you some do's and don'ts. Welcome back. Here, I have an example problem, and looking at it, the problem states, let f be a differentiable function such that f of 1 equals 9 and f prime of 1 equals 5. What is the approximation for f is 0.85, found by using the line tangent to the graph of f at x equals 1. So to start, I identified the point of tangency, which is 1, 9, and that is the first do. And next, I then found what the slope is, which it's given in the problem, it equals 5. And next, I used the equation of the tangent line, and I used it in point slope form, which is a second do. So y minus 1, y minus y1 equals m x minus x1. So you get y minus 9 equals 5 x minus 1. Then I rearranged it so that I could solve for y, which gave me this equation right here. From there, I can just plug in 0.85 and solve from there. So I simplified it down in these steps, and it got me 8.25. And when I'm done, I'm going to check for reasonableness, which is our last do. So the problem, it tells us that the slope is positive 5, and we're looking at f of 1, which equals 9. So if we're looking at before f of 1 at 0.85, the y value should be lower than 9 because the slope is positive. And to some don'ts for the problems is using the tangent x to find what 0.85 would have been. We do not want to put 5 into this y value here. And also, don't ever forget y1 in your equation, and don't ever flip x minus x1 to x1 minus x.